Let's see energy band for semiconductor, metal and insulator. In case of metal, there is overlapping overlapping of conduction and valence band. This one is valence band and the upper one is conduction band. This is conduction band and this one is valence band, and this is the overlapped portion of conduction and valence band. This is the case for metal. Now in case of semiconductor, we have already seen that there exists a gap between conduction and valence band, and that gap is called forbidden energy gap, denoted by Eg. This is conduction band, this one is the valence band. And in case of insulate, this is the case for semiconductor. And in case of insulator, the gap between conduction band and valence band is large. Large mean to say it is of the order of 5 to 6 electron volts, which is large as compared to the energy gap in case of semiconductor. This is forbidden energy gap, which is 5 to 6 electron volts. This is the energy band diagram for insulator. Now if I write the order of conductivity, then conductivity of metal is maximum, and then we have conductivity of semiconductor, and conductivity of insulator is minimum. Now let us see the current density in metals. If we have a piece of conductor with cross sectional area A and length of conductor is L, this conductor is connected to the excitation external voltage V, or make it E, better to write V. V, and capital N is the number of free electrons or valence electrons, because in case of metals, valence electrons are the conduction or free electrons. This conductor has N electrons. Because this conductor is connected to the excitation, so due to this excitation, all electrons are drifted in one direction. All electrons are drifted from right to left side, and current will flow in the opposite direction. This is the direction of current through conductor. The drift velocity drift velocity is Vd. This is mu into E, where mu is the mobility of electrons. Mu is the mobility of electrons. E is the applied electric field. And Vd is the drift velocity. So this mobility is basically Vd by E, and the unit for mobility is meter per second into volt per meter. So the unit for mobility is meter square per volt second. This is the mobility. Now the current density in case of metal is denoted by J. This is current flowing per unit area, that is ampere per meter square. Now this current is charge upon time, and total number of charge is N into Q, total charge, divided by time. This is the current into 1 by A. Now T is the time required for electrons to cross or to cover length L. So the expression for current density is NQ by A, and time is replaced by L by Vd. L is the length of conductor, and Vd is the drift velocity. So the current density is NQ Vd divided by A into L, where capital A is the cross-sectional area of the conductor, L is the length. So basically product of A and L is the volume volume of the conductor. N is the number of electrons. So N by Al is number of electrons per unit volume, and this is denoted by small n, that is number of electrons per unit volume, and it is called concentration of electrons. And its unit is per cubic meter. So the expression for current density is now J, that is NQ into Vd, and this N into Q, N is the concentration of electrons per unit volume, so NQ is the charge of electrons per unit volume, charge of electrons per unit volume. So charge of electrons per unit volume is also denoted by rho v, and its unit is coulomb per cubic meter. So the expression for current density is rho v into Vd. Now this Vd, again better to write Nq in place of rho v. Current density is Nq. Vd is the drift velocity, that is mu into E. So this NQ mu is conductivity. Conductivity is NQ mu. So here Q is charge of electron, mu is the mobility of electrons in metal. So we can say conductivity, Q and mu are constant, so conductivity is proportional to N. Conductivity is proportional to concentration of electrons. In case of metals, this concentration of electrons is of the order of 10 to the power 29 per cubic centimeter. And in case of semiconductor, the concentration of electrons is of the order of 10 to the power 10 to 10 to the power 13 per cubic centimeter. And in case of insulators, the concentration of free electrons is very small. This is around 10 to the power 6 per cubic centimeter. So we can see that concentration of electrons in metal is very large, so its conductivity is also large. And in case of insulator, concentration of electrons is very low, so its conductivity is also very low. Now let us see let us see intrinsic semiconductor, or better to start with new page. intrinsic semiconductor. Intrinsic means pure, without impurity or without doping. See, the two popular, in fact, three popular semiconductors are silicon, germanium, and gallium arsenide. Silicon and germanium both are tetravalent. Now we can draw the two-dimensional symbolic representation of crystal structure of semiconductor. Each atom is surrounded by 4 electrons. And each electron is shared by the neighboring ions, and this will form a covalent bond. This is covalent bond, and these electrons are valence electrons. So this is the two-dimensional symbolic representation of crystal structure of semiconductor. At absolute temperature. Now the same can be represented, or same can be shown in terms of band diagram. In case of semiconductor, we have two bands, conduction and valence band, and at absolute temperature all electrons are at lower energy state, or all the electrons are part of valence band. So these electrons are valence electrons. They are the part of covalent bonds. This is the energy band diagram of semiconductor, intrinsic semiconductor. Now, if temperature is increased, if temperature is increased to room temperature, then what will happen? Then due to thermal energy, electrons will break the covalent bonds. This is broken covalent bond. This is broken covalent bond. And this is hole, and this one is the free electron. This we can show in the energy band diagram also at room temperature. room temperature or 300 Kelvin, the electron will jump to the conduction band. From valence band, electron will jump to the conduction band, and this will create a hole. Sorry. This will create a hole in the valence band. Holes will exist only in the valence band. This is free hole in valence band, and this one is the free electron or conduction electron in conduction band. And due to the flow of conduction or free electron, current will flow through the semiconductor. This is symbolic representation, and here we can see that number of electrons in conduction band is same as the number of holes in the valence band. So still this is intrinsic semiconductor, because concentration of electrons in conduction band is same as the concentration of holes in valence band, and that is equal to intrinsic concentration. See, one more thing we can see here, that in conduction band, this free electron is not surrounded by any other charged particle. So the mobility of electrons mu n in conduction band, mu n is the mobility of electrons in conduction band, and mu p is the mobility of holes in valence band. The free electron in conduction band is not surrounded by any other charged particles, and in valence band this hole is surrounded by all the valence electrons. So mobility of electrons in conduction band is greater than mobility of holes in valence band. The intrinsic concentration for silicon Ni is, at room temperature, it is 1.5 into 10 to the power 10 per cubic centimeter, and for germanium intrinsic concentration is 2.5 into 10 to the power 13 per cubic centimeter. For and the mobility for the case of silicon, mu n is the 1300 centimeter square per volt second, and mu p is 500 centimeter square per volt second, and for germanium mu n is 3800 centimeter square per volt second, and mu p is 1800 centimeter square per volt second. All the information provided here is at room temperature. Now let us see extrinsic semiconductor. In case of extrinsic semiconductor, this is the semiconductor with doping. Now we have two types of doping. First is pentavalent or donor impurity, and second is trivalent or acceptor impurity. Phosphorus, arsenic, antimony, bismuth are the pentavalent impurities, and boron, aluminium, gallium, indium are the trivalent impurities. If intrinsic semiconductor is doped with only pentavalent impurities, then this will make n-type semiconductor. And if semiconductor is doped with only trivalent impurities, then this will make p-type of semiconductor. So let us see the crystal structure and band diagram for extrinsic semiconductor with pentavalent impurity or n-type semiconductor doped with pentavalent or donor impurity. If I draw the two-dimensional symbolic representation of crystal structure of semiconductor doped with pentavalent impurity, then this will look like this. This +5 is pentavalent impurity. In the outermost orbit of this pentavalent impurity has 5 valence electrons. So out of 5, 4 will participate in the covalent bond, and the 1 electron will left unengaged, and that will be access free electron. So this is the donor ion. And this electron is excess free electron. Now we can show this in the form of in Venn diagram also. Conduction band, valence band, and this is EI, intrinsic energy level. The donor energy level is very close to the conduction band. This gap, this is ED's donor energy level. Sorry. Donor energy level, and this gap is very small. This gap is 0.05 electron volts for silicon, and it is 0.01 electron volts for germanium. Valence band is full of valence electrons, and if intrinsic semiconductor is doped with pentavalent impurity, so then there exist excess free electrons at the donor energy level, and this excess free electron can easily jump to the conduction band, and these conduction electrons can contribute to the conduction current. So in N-type, the semiconductor is called N-type semiconductor because electrons are in majority. Electrons are majority charge carriers. And semiconductor is N-type. Now let's see the crystal structure and energy band diagram. If semiconductor is doped with trivalent impurities. Semiconductor doped with trivalent or acceptor impurity. So if trivalent impurity is doped in intrinsic semiconductor, then the acceptor ion has only 3 valence electrons in the outermost orbit. So in covalent bond there is a deficiency of electron in the acceptor ion, and that is excess hole. Sorry. This is excess free hole. This we can show in the band diagram. Now in case of acceptor impurity, the acceptor energy level is close to the valence band. This is EA, acceptor energy level, and again the gap between acceptor energy level and valence band is very small, that is 0.05 electron volt for silicon, and it is 0.01 electron volts for germanium. These valence electrons in the valence band can easily jump to the acceptor energy level, and while doing so they will create holes in the valence band. Sorry. Here in the valence band holes are created. So we can see that holes are in majority. Hence the semiconductor is N-type, or sorry, P-type. This will make P-type semiconductor. Now if the semiconductor is doped with both types of impurity, semiconductor doped with donor end and acceptor impurity. Let us consider the first case. If donor impurity concentration is very large as compared to acceptor impurity concentration, In that case, electrons are majority charge carriers, and the concentration of majority charge carriers is Nd. Now by mass action law, product of N into P is Ni square. So the minority charge carrier concentration is Ni square by N, that is Ni square by Nd. Electrons are majority charge carriers and holes are minority charge carriers. So semiconductor is N type. Now second case, if the acceptor impurity concentration is very large as compared to the donor impurity concentration, then concentration of holes is Na and holes are the majority charge carriers, and concentration of electrons is Ni square by P, that is Ni square by Na. Electrons are minority charge carriers. So semiconductor is P type. Now the third case, if semiconductor is doped with both acceptor and donor impurities, and donor impurity concentration is large as compared to acceptor impurity concentration, but it is not very large. Nd is not very large, but large as compared to Na. In that case, concentration of free electrons is Nd minus Na. Still, electrons are in majority. And the concentration of holes is Ni square by N. So it is Ni square by Nd minus Na. And holes are in minority. So semiconductor is again, this will be N type semiconductor. Now if Na is large, fourth case, if Na is large but comparable with Nd, in that case concentration of free holes is Na minus Nd and holes are in majority. Concentration of free electrons is Ni square by P, that is Ni square by Na minus Nd, and electrons are in minority. So semiconductor is again P type. Now if semiconductor is doped with equal amount of acceptor and donor impurities, in that case acceptor and donor will neutralize each other and semiconductor will remain intrinsic semiconductor. Semiconductor is